Somewhere in the world right now, a machine roughly the size of a bus is doing something that sounds almost like science fiction, using light to draw patterns thinner than a virus over and over, thousands of times a second, onto a wafer of silicon that will eventually become the processor. Inside your next phone or laptop, there are only a few hundred of these machines on the entire planet. One company builds all of them. And without that company's technology, the most advanced chips made today simply wouldn't exist, no matter how much money or ambition any other company brought to the problem. To understand why that's true, it helps to start with something much simpler than the machine itself. What actually has to happen to turn a plain blank piece of silicon into a working chip? A chip isn't built by carving or assembling tiny pieces the way you'd build something out of physical parts. It's built by repeatedly printing incredibly precise patterns onto the surface of a silicon wafer, layer after layer, each layer defining a piece of the electrical circuitry that will eventually let the chip calculate, store, and move information. Do this correctly dozens of times, with each layer aligned perfectly on top of the last, and you end up with a working processor containing billions of microscopic components. Get even one layer slightly wrong, and the entire chip can fail. The tool responsible for printing each of those layers is called a lithography system. And the basic idea behind it is easier to picture than you'd expect. Imagine a photographic slide projector, the kind that shines light through a transparent image to project it onto a screen. Except here, the screen is a silicon wafer coated in a light-sensitive material, and the slide, called a mask or sometimes a reticle, contains the intricate pattern of one layer of the chip's circuitry. Light passes through the mask, carrying that pattern with it, and a system of lenses focuses that pattern down to an almost unimaginably small scale before it lands on the wafer. Wherever light hits the light-sensitive coating, a chemical reaction marks out exactly where the next manufacturing step should add or remove material. Repeat that process, layer after layer, and the blank wafer slowly becomes a finished chip. For a long stretch of semiconductor history, this process used ordinary ultraviolet light, and steadily smaller features were achieved mostly by refining the lenses, the light source, and clever tricks for squeezing more precision out of that same basic wavelength of light. But there's a hard physical limit to how small a feature you can print using light of a given wavelength. Roughly speaking, you can't reliably draw a line much thinner than the wavelength of light you're using to draw it. In the same way, you can't paint a razor-thin line with an unusually thick brush no matter how careful your hand is. As chip designers pushed towards smaller and smaller features, chasing more transistors packed into the same physical space, they eventually ran up hard against that limit using the older generation of ultraviolet light. The industry needed a fundamentally shorter wavelength of light to keep shrinking chip features further. And that need is exactly where this story turns from ordinary manufacturing refinement into one of the most difficult engineering problems the entire tech industry has ever solved. The answer is a light source using an extremely short wavelength, just 3.5 nanometers, known as extreme ultraviolet light, or EUV. That number alone doesn't mean much on its own, but the contrast is worth sitting with. 3.5 nanometers is roughly 14 times shorter than the light used in the previous generation of chip-making equipment, which is exactly the kind of jump needed to keep printing meaningfully smaller features. The company that turned this idea into a working, reliable, mass production machine is ASML, a Dutch company that spent roughly 2 decades and an enormous amount of money solving a series of engineering problems that individually sound almost absurd in their difficulty. Start with the light itself, because at this wavelength, light doesn't behave the way people are used to thinking about it. Extreme ultraviolet light of this wavelength doesn't exist in any convenient, naturally produced form. You can't simply build a bulb that emits it. Instead, it has to be generated by firing a high-powered laser at microscopic droplets of molten tin, vaporizing each droplet into a plasma hot enough to emit the exact wavelength of light needed. And this isn't a one-time event. It happens roughly 50,000 times every single second. Each droplet only a few millionths of a meter across, hit twice by precisely timed laser pulses to shape, and then vaporize it at exactly the right moment, generating a tiny, extraordinarily brief flash of usable light. Missing the droplet, mistiming the pulse, or vaporizing it incorrectly means that flash of light simply doesn't happen, and the whole system depends on getting this right tens of thousands of times per second, continuously, for the machine to be useful at all. The next problem is almost as strange. This light is so easily absorbed by ordinary materials that it can't pass through conventional glass lenses, the way visible light does. Regular optical lenses, the kind used in the earlier generation of lithography machines, simply don't work at this wavelength. The light gets absorbed before it can pass through. So, instead of lenses, EUV systems use an elaborate series of extraordinarily precise curved mirrors to guide and focus the light, reflecting it at carefully calculated angles until it eventually reaches the silicon wafer. These mirrors have to be polished to a level of smoothness where an imperfection just a few atoms tall would meaningfully distort the pattern being projected, and even then, at this wavelength, a meaningful fraction of the light is lost or absorbed at every single reflection along the way. That means the system has to start with a tremendous amount of usable light, since only a small percentage of it survives the entire journey through the mirror system to actually reach and pattern the wafer. The mask itself deserves a moment of attention, because it's easy to picture it as a simple stencil, and it's anything but at ordinary ultraviolet wavelengths. Masks are transparent, letting light pass through open areas and blocking it elsewhere, much like a photographic slide. At extreme ultraviolet wavelengths, no material is usefully transparent. The light gets absorbed almost immediately by anything it passes through. So EUV masks work by reflection instead of transmission, built from dozens of alternating ultra-thin layers of different materials engineered to reflect this specific wavelength of light efficiently, with the actual circuit pattern etched into an absorbing layer on top that blocks light in some areas while letting it reflect in others. Manufacturing one of these masks is itself an extraordinarily precise process, since any defect in those dozens of underlying reflective layers, invisible to the naked eye, can print as a real flaw on every single chip manufactured using that mask. Multiplied across every wafer run through the system. The light source and mirror system evolved over a genuinely long timeline before any of this became practical for mass production. Early experimental versions of extreme ultraviolet light sources were far too weak and unreliable for commercial chip making, producing only a fraction of the light intensity needed to expose wafers fast enough to be economically useful. Getting from those early experiments to a light source stable and powerful enough to run continuously inside a working factory took roughly 2 decades of engineering refinement, several different approaches to generating the plasma that produces the light, and the enormous ongoing investment from both the equipment maker and its largest customers, some of whom invested directly in the technology's development years before a single, commercially useful machine existed, simply because the entire future of their own manufacturing roadmap depended on this specific engineering problem eventually being solved. Because the entire process has to happen inside a vacuum. Extreme ultraviolet light is absorbed by ordinary air itself. meaning the light source, the mirror system, and the wafer all have to sit inside a chamber with essentially no air present at all, adding an entire layer of engineering complexity around containment, precision movement, and contamination control, since even a microscopic speck of dust drifting into this vacuum environment could ruin a pattern being printed onto a wafer worth an enormous amount of money. Once the light finally reaches the wafer, the printing process itself has to repeat this entire sequence. Mask, mirrors, light, wafer, accurately and consistently across dozens of separate layers for a single chip design, with each layer aligned to the previous one, with a precision far finer than the width of the features being printed. A single misalignment between layers, even by a distance smaller than what most manufacturing tolerances anywhere else in the world would consider meaningful, can mean an entire chip fails to function. Manufacturers run this sequence across an enormous number of wafers every single day, and the machine performing this entire process has to do it reliably, hour after hour, for years, since any unexpected downtime on a lithography line can idle an enormous amount of expensive downstream chip manufacturing capacity that depends entirely on that one machine's output arriving on schedule. This is why so few companies in the world make this equipment at all, and why, for the most advanced category of chip manufacturing specifically, there is currently only one company capable of producing machines that do this reliably at the scale the industry needs. Building a working EUV system required, solving the plasma light source problem, the mirror precision problem, the vacuum containment problem, and the manufacturing consistency problem simultaneously, drawing on specialized expertise in optics, laser physics, precision mechanics, and material science that took decades to develop and that isn't easily replicated by simply investing enough money in a shorter time frame. Competing companies that might otherwise build rival lithography equipment have largely stayed focused on less extreme categories of chip making, where older, more established lithography techniques remain sufficient, leaving the most advanced, EUV-dependent frontier of chip manufacturing served by essentially one supplier. That concentration creates a genuinely unusual choke point running through the entire global technology industry. Every company that wants to manufacture the most advanced processors, the chips inside flagship phones, high-performance computing systems, and the accelerators powering today's largest AI models, ultimately depends on securing access to a very small number of these machines, each one taking a long time to build, install, and calibrate at a customer's facility once ordered. A handful of the world's most advanced chip manufacturing facilities, spread across a small number of countries, represent nearly the entire customer base capable of using this category of equipment at the frontier of chip manufacturing. That's an extraordinarily narrow funnel for an entire global industry to depend on, and it means decisions made about who can purchase this equipment, how many machines can be built and shipped in a given year, and which countries are permitted to receive them, have become matters of serious economic and political weight, well beyond ordinary industrial equipment sales. Picture that funnel as an actual map, because that's the clearest way to see how narrow it really is. The equipment itself is designed and assembled primarily in one country in Europe, drawing on a supply chain of highly specialized component makers spread across several other countries, each contributing some piece too difficult or too specialized for even the equipment maker itself to build entirely in-house. Precision optics from one specialized supplier, laser systems from another, ultra-stable mechanical stages from yet another. Finished systems then shipped to a small number of customer countries in East Asia and the United States, home to the handful of facilities in the world equipped to actually operate them at the most advanced tier of chip manufacturing. Every one of those shipments involves careful coordination. since each machine takes months to transport, install, and calibrate on-site before it can begin reliable production. And every customer country represents a substantial share of the global supply of the most advanced chips made anywhere on Earth. That narrow map is exactly why this equipment has become entangled with international politics in a way most manufacturing tools never do. Export regulations in the country where the equipment is made, shaped in coordination with allied governments, determine which countries and which specific customers are permitted to receive the most advanced versions of this technology at all, treating access to these machines as a matter of strategic significance rather than ordinary trade. A country or company denied access to the newest generation of this equipment doesn't simply fall slightly behind. It can find itself unable to manufacture the most advanced tier of chips at all, regardless of how much money or engineering talent it has available, because no substitute technology currently exists that can replicate what these machines do. That single dependency has turned lithography equipment into one of the most closely watched categories of trade policy in the entire technology industry. It also means the pace of progress in chip manufacturing is, in a very real sense, tied to the pace of progress inside one company's engineering roadmap. Every future generation of smaller, more powerful chips depends on lithography equipment capable of printing correspondingly smaller features, which means every future leap in chip capability is quietly gated behind whether the next generation of this specialized equipment can be engineered, built, and deployed on schedule. When people talk about the pace of progress in computing slowing down or speeding up, they're often really talking, whether they realize it or not, about the pace of progress happening inside this single, extraordinarily specialized category of manufacturing equipment. There's also a scale problem sitting underneath all of this that's easy to underestimate. A single one of these machines isn't a cheap purchase, isn't quick to build, and isn't something a factory can simply order and receive off a shelf. Each system is effectively custom assembled, tested extensively before it ever leaves the factory where it was built, then disassembled into a large number of separate components for shipping, since a finished machine is far too large and delicate to transport in one piece. Once it arrives at a customer's facility, a specialized team spends a substantial stretch of time reassembling and calibrating it on-site, checking and rechecking alignment across every mirror, every stage of the light path, and every mechanical system that positions the wafer with the precision this process demands. Only after that lengthy installation process is the machine considered ready for full production use. That timeline means a customer's manufacturing roadmap has to be planned years in advance around exactly when new machines are expected to arrive and come online, since there's no way to simply speed up the process by ordering more machines on short notice. The equipment maker's own production capacity for building these systems is itself limited by the same kind of specialized component supply and precision assembly constraints found everywhere else in this story. This is also why the entire industry watches this one company's product roadmap so closely in a way that has few real parallels elsewhere in manufacturing. A delay in the next generation of this equipment doesn't just affect one customer's plans, it can quietly reset the expected timeline for an entire generation of future chips across the whole industry, because every major chip manufacturer's own roadmap for smaller, faster, more efficient processors assumes that the lithography equipment needed to print those chips will be available roughly on schedule. When that assumption slips, entire product categories, from smartphones to AI accelerators to the servers powering cloud computing, can end up quietly delayed as a direct consequence, even though none of those companies had anything to do with actually building the equipment their entire business ultimately depends on. So the next time a new processor is announced with smaller, more efficient, more densely packed transistors than the generation before it. Remember what actually made that possible, before any chip designer ever touched the specifications. Somewhere, a machine the size of a bus fired a laser at a droplet of molten tin 50,000 times a second, bounced the resulting light off. A series of mirrors polished to near perfection inside a vacuum chamber and printed a pattern finer than most people will ever be able to picture. One layer at a time, one wafer at a time, using a technology that only one company in the world currently knows how to build.